Hi everyone, welcome to this channel. In this video today we'll discuss about rectangular dielectric resonator antennas. So after that we'll design the RDRA using CST MWS software. So let's start this video. So as you know that dielectric resonator antenna is a radiating element which radiates the electromagnetic signal into free space. It is also called as transducer, which convert one form of energy to another form of energy and vice versa. So this rectangular dielectric resonator antenna consists of three main parts. So first layer is ground plane, above the ground plane substrate, then above the substrate dielectric resonator. So we can say that dielectric resonator is the heart of dielectric resonator antennas because this dielectric resonator is the radiating element of dielectric resonator antennas. So it mainly consists of three layers. Next we will discuss about the empirical formula, how to get the dimension of rectangular DR like length, width, height at a particular resonant frequency. So this is the empirical formulas for RDRA. So here we will calculate the resonant frequency after knowing the F value, W and epsilon RDRA, that is dielectric resonator permittivity. So after getting the F value, that is normalized frequency, we can easily find the resonant frequency, or also by taking this resonant frequency we can determine the length, width, height of the dielectric resonator antennas. So here we'll find the coefficient, that is x0, x1, x2. So after finding the x0, x1, x2, then we can find the normalized frequency, that is capital F. So after getting the F, we'll determine the resonant frequency. So at 5.9 gigahertz frequency, I have determined the length, width, height of the dielectric resonators, rectangular dielectric resonators, by using these empirical formulas. So this is not only 5.9 gigahertz frequency, you can design the terahertz frequency also and millimeter wave frequency also. Any frequency we can design by using this empirical formula. So let's start our design by using CST MWS software. So I will explain step wise from starting to end and how to determine the different parameters of the rectangular dielectric resonator also. So let's start. So this is CST Studio Suite. So first of all, we have to click this no option over here. Then we have to click new template. Then here different options are available. So as we are going for antenna design, that is microwave frequency range, so we need to click this microwave and RF and opticals. So here we can design up to optical range of frequency. Then EDA, electronics, EMI, EM, C. So different options are available. So we need to click this MW and RF optical. Then antenna, here also different options are available. So we are going to design the antenna, so we need to click this antenna. Then next. So here planar, wire, phased, mobile, reflector. So as we are going to design the dielectric resonator, so we need to click this dielectric resonator, that is DR. Here the time domain and frequency domains are available. So this time domain is mainly used for the wideband frequency range, and frequency domain is mainly used for the narrowband frequency. So as the dielectric resonator antenna provides wideband frequency, so we need to click this time domain analysis or time domain solver. Then next, so this is the unit, dimension, frequency, time, temperature. So we need to check whether dimension is mm or cm and frequency is terahertz or gigahertz. We need to check this, both the options. This one is mm and frequency is gigahertz. Then next, so here as we are going to design 5.9 gigahertz frequency, so we need to take the minimum frequency, that is 4.9, and the maximum frequency is 6.9. so monitor is electric field. We need to check the electric field, magnetic field and far field. So the frequency is defined as 4.9 lower frequency, 6.9 higher frequency and 5.9 is the middle frequency, that is our resonant frequency. So then next, finish. So this is our workflow. Here first of all we need to set the local coordinate. This is our x, y, z axis, and this is our coordinate systems x, y, z. And this one is the origin points. So in order to better visualize of the geometry, we need to disable this working plane. Okay, this is our coordinate axis. Then as the dielectric resonator antenna consists of 3 layer structure, first layer is ground plane, then substrate, above the substrate dielectric resonator. So first of all we'll design the ground plane. So we need to go to the modeling, and here we need to click this brick. So this one is a ground, and so this one is minus 25 plus 25 minus 25 plus 25 0, and thickness is 0.035, and this is component 1 that will save, and here we will take PEC or we can take the copper material also. Then click the OK. So this is our ground plane. So if you want to change the color, then click this one, ground, right click and go to the change material and color. So we can take any of the color. Okay, so this is our ground plane. So above the ground plane we need to design the substrate. Again we go to the brick, then substrate. So this dimension is also minus 25 plus 25 minus 25 plus 25. This height should be start from 0.035, and this one is 0.035 plus height is 1.6. So here we will take the material is FR4 material, which is easily available in the market. That's why we are taking the FR4 material, FR4 lossy material. So the permittivity or epsilon of the FR4 is 4.3, and electric tandem loss is 0.025. You need to click this one. So FR4, then OK. So this is our first layer, and this one is our second layer, that is substrate. So if you want to change the color, again you click this one, substrate, change material and color. We can take this color also. first layer, second layer. Then third layer is the dielectric resonator. Again we need to click this brick. Then this one is dielectric resonator, and the dimension is, that is 11. So we need to take minus 5.5 to plus 5.5, and here also minus 5.5 to plus 5.5, and this one is this one should be 0.035, this is ground, plus 1.6, that is your FR4 materials. Then here maximum height, that height is, we have already calculated, that is 8.5. And so in this case we are taking the aluminum material, that is 99.5% alumina, and their dielectric constant is 9.9, and Tyndall is 0.0001. so this one is very much important whenever we will calculate the parameters, different dimensions of the rectangular dielectric resonator antenna. So in the empirical formula this one is required, this epsilon r. So this aluminum material also easily available in the market. Then preview, then okay. So this is our DR. So first layer is the ground, second layer is the substrate, and third layer is our dielectric resonator. Then press M. So we need to select this middle point over here, or otherwise you can go for this peak points and click this peak edge center, that is M. So this one is the center peak edge center. So if you go to the align WCS, then automatically our coordinate axis will set over here. Then we need to design the microstrip feed, which will give the input excitation to the dielectric resonator. So again here we need to click this bricks, and we need to design the microstrip feed. This one is feed. So here I have already calculated the feed length and width as per the 50 ohm impedance. So formula also available, so you can refer the CA Balanis. All the formulas are available how to calculate the width of the microstrip feed. So here we will take the minus 3.7 divided by 2 plus 3.7 divided by 2, and V will start from 0 to 20.5. so at 20.5 this microstrip feed and antenna both are perfectly matched 50 ohm impedance. So for the newcomers or those who have designed newly, so they can optimize the microstrip feed by taking the different length of feed. This is this one should be 0, and this is 0.035, and here we'll take the PEC material, or we can take the copper material also. Then okay. So this is our feed. So we need to give some different color in order to avoid the confusion. Okay. Then next is our SMA connectors or coaxial probe. So different types of excitations are available. So we can use the waveguide port, discrete port, or we can use the coaxial probe also. So here we'll design the coaxial probe. So here no need to design the coaxial probes because it is already available in CST. So I will tell the step how to bring that coaxial probes. Okay. So first of all we need to set this coordinate axis. This W should be towards the feed length actually. So accordingly our coaxial probe will set. So if we'll take like this, then the feed inner conductor of the coaxial probe will move towards the W axis. That's why we need to rotate this W into 90° over here. So for this we need to go to the transform option, and here we will rotate this W axis. So this one is rotated. Okay, then is this OK option over here. Okay, this W axis is towards the feed length. Now we'll go to the home, and here macros options are there. Then we'll go to the calculate analytic line impedance. Then here coaxial probe is available, so we need to feed the capital D, that is the diameter of the dielectric, and this is the diameter of the inner conductor. Then we need to check whether Z0 is nearly about 50 or not. Okay, so this one is 1.2. Okay, now our coaxial probe is designed, so we need to set this length. We need to, because this coaxial probe will start from this point onwards, so we need to bring backside the complete coaxial. It need to bring backside. So control T, that is transform option is available over here, this one. So we need to bring backside. How much? That is 0.5, because the total this length is 1 mm, so we need to bring the minus 0.5. so okay, so similarly we need to so this one should be start from this point onwards, so we need to shift the offside also. Again we need to take this one and transform, and this one should be minus V, that is minus 1.21 divided by 2. Then okay, then again check it. So this one is touched with this inner conductor, is touched with our microstrip feed. Okay, so and then we need to set this length and all these things. So then inner conductor, W length minus 2, and this one is 3 preview. Okay, similarly we need to set this dielectric also. Then outer conductor, okay, so everything is over. So now we need to give the input excitation. So for this we need to press F and click over here. Then waveguide port, this is okay. Okay, input excitation is given. So now we'll check the setup solver, everything is okay or not. Accuracy is minus 40. Then we'll start the program. So before starting of this program we need to save this one actually. So as per your figure or as per your antenna, we need to save the antennas. Okay. Now the simulation is going to complete. Okay, completed. So now the simulation is completed. So let's check the results. 1D results. This is S parameter. So this is our S parameter. So our impedance band will start from this point. This is press M and we will need to click over here. This one and press. Okay, so this is our impedance bandwidth, and our main resonating frequency, it is over here, it is 5.93. so in calculation also, theoretical calculation also, we got 5.9. in simulation also we got 5.9. so like that we can check. And here different options are available. We need to find the efficiency also in a linear scale. So if we improve this S11 parameter, then our efficiency also improve. So like that we need to check. And also we can check the our real part and impedance part, whether it is 50 matched or not. All these things we need to check over here. Okay, so and also we can by optimizing the dimension of the RDRA and feed, we can bring the more accurate results, or we can improve the S parameter also. So here the return loss is now minus 21 or 22, nearly about 22. So we can improve also by optimizing the feed length, width, and our dimension of dielectric resonator. So, and we can check the far field result also here at 5.9. This is our gain is 6.7 dBi at 5.9 gigahertz frequency, and sorry, this is the directivity, and this is gain is 6 dB IEEE, and realized gain is 5.97 dB. And we can check the polar plot, this one at cut 90, or we can say that this one is our YZ plane. And if you go for cut 0, then this one will be XZ plane. This is XZ plane and another is YZ plane. So like that we can check all the parameters of the rectangular dielectric resonator antenna. So thank you. If you have any doubt in the comment section, you can write the question or queries, so I can help you. And if you need any information regarding the rectangular dielectric resonator antenna, so I can provide the soft copy of RDRA design also. So thank you.